Right.
Okay, great.
So you should see it.
That brings us to the last speaker of the workshop, Ted Yoder from IBM. Ted is going to tell us about some joint work with Raul Sarkar about a graph-based formalism for surface codes and twists.
Yeah. Hi, everyone. Thanks, Steve. Thanks, the rest of the organizers for setting this conference up, even under the circumstances. I hope everyone's not craving bacon and waffles too much for their lunch or dinner, and you can stick around for this talk. Yeah, so as Steve said, this is joint work with Rahul, who is a PhD student in math at Stanford. And this is about a graph-based formalism for surface codes and twists. So what do I mean by this? So there's a bunch of different models of 2D surface codes in the literature. For instance, Brabi Kataev was basically the first 2D planar surface code, as you can see in the bottom left here. And then this was, rotated by Bombin and Martin Delgado to get the picture in the top right here, which uses half the number of qubits to encode the same number of qubits with the same distance. And then, there's even other models of surface codes, like for instance, this twisted model introduced by Bombin, where there are now some weight 5 stabilizers and a chain of like mixed X and Z type stabilizers connecting them. And this twist idea has sort of grown into to encompass other models. For instance, I have a work with Isaac Kim, where we essentially move this twist defect into the middle, and now all the stabilizers are weight 4. Kesselring et al. Sort of generalized even this triangle code idea into more general stellated codes with larger symmetry. And then there's even other models of twist defects, like this one appearing in the wormhole paper by Krishna and Poulan, where you simply measure like two qubit operators to create your twist defects. So basically the motivation for this work is, there's all these models of twist defects. What do they have in common? Can we sort of unify them under one model? Yeah, so that's the objective of this talk, and that's what we succeed in doing. So like, what are some motivations for doing this? Well, I mean, the previous slide was sort of one motivation, is just that it seems, theoretically pleasing to sort of unify all these models. If you're interested in some like consequences of that, this could, for instance, organize the search for better surface codes, where we are constrained by this n being proportional to kd squared bound of Brabi, Poulan, and Terhall, but we can improve that constant c. And that was kind of the motivation for at least my work with Isaac Kim, where we were able to achieve like c equals 3/4, whereas the rotated surface code just has c equals 1. So you want c to be small. Some other motivations are, well, once you have this model, maybe you can classify these codes. Think in terms of topological phases, or the topology of their logical operators. And then finally, if you have all the codes under one framework, then you can start thinking about relating them using some pocket groups. So mostly in this talk, I'm going to be focusing on number 1, and backing it up with a bunch of examples and such. Okay, and so those were sort of the theoretical reasons to consider this. Maybe you care about practical consequences, and we probably should, but this is out of scope of this presentation. So one question that this unification can help us answer is what connectivity might be worth pursuing, and maybe that's a bigger bigger question for some architectures than others. You know, we just heard the photonics can sort of adapt pretty easily. But so if I tell you that you can use fewer qubits by putting building a code on the torus, is it worth like actually building the torus? Also, once we have all this set of codes, we can then investigate what sort of gates are easy, and this will also factor into what code we should choose. So it might be the case that you can allow your logical operators to be accessed on the sort of boundary of your patch of code, and that would allow you to do some sort of lattice surgery operation. It also might be the case that you can leave space to sort of braid these twist effects and do some Clifford gates that way. And then finally, maybe we can come up with decoders to decode like the whole family of codes. And this, you know, these may require some code specific optimizations. We have some ideas in this direction, but it's sort of unclear. So this is, you know, I say out of scope of this presentation, but it's some things that the work hopefully inspires people to think about. Okay, so what is the basic outline of this presentation? Well, what we have to start with is an embedded graph into some 2D manifold. And we're gonna just allow that manifold to be anything. It can have arbitrary genus, and it can be orientable or non-orientable. And then from that graph, we're gonna define a Majorana surface code by assigning Majoranas to like 2 Majoranas to every edge, and then also some at the odd degree vertices. And then you can take the Majorana code and you can associate qubits with some subsets of the Majoranas, and in this way get a qubit surface code from the Majorana surface code. Or you can sort of bypass the Majorana surface code entirely using something that some set of polys that we call a cyclically anticommuting set. And so I mean, in that way, if you're not comfortable with the Majoranas, you can just get your qubit surface code. And then, so once I describe the construction to you, I'll talk about how many logical qubits it encodes. Also, definitely give some examples. I think that's probably the most exciting part. And then talk about bounds on the code distance that we can give. Okay, so how should we describe embedded graphs? So, I mean, one way to describe the graph, I guess, is to just draw it. I mean, these are 2D, and if we want to embed it on the torus, for instance, we can just draw this fundamental polygon, identify the edges, and draw the graph. And that's fine, like if we're just describing a specific code, specific graph. But because we're describing like this whole family, it's really nice to just have this formalism in place. So what we're using is called rotation systems. So it's a combinatorial description of a graph embedding. It consists of a set of half edges and then 2 different permutations, where new is just an arbitrary permutation of that set of half edges. The permutation epsilon has to square to identity. And it's just once you have these things, it automatically defines an embedded graph. So the vertices of the graph end up being orbits of nu, as you can sort of see in this picture on the right. And then the edges end up being orbits of epsilon, and the faces end up being orbits of nu composed with epsilon. And then you can just count the number of these orbits, and you can figure out the genus of the surface in which your graph ends up embedding. So this is the description for orientable manifolds. I decided just to show this to you. For non-orientable manifolds, long story short, you introduce you introduce another permutation. Yeah, I'm not going to get into it.
Sorry, Ted, can I just ask a
Yes,
question?
yes. No
The
problem.
set of half edges, is that the
Yeah.
full set of half edges on the whole graph, or is there some kind of like vertex transitive action that you insist on?
Right, so this is the full set of half edges, and then um, the group generated by nu and epsilon should be transitive. So you should be able to map any half edge to any other half edge using nu and epsilon. That just ensures the graph is connected.
Okay.
Hope that answers your question.
Yeah, I think it does. I'm looking forward to seeing an example.
Right, okay. um, so using this rotation system framework, we'll define Majorana codes. So if you aren't familiar with Majoranas, I guess it's a set of operators. They all anti-commute with each other. If you want to define a code using these, then you, just like for Pauli stabilizer codes, you need to define a stabilizer group, and minus identity should not be a part of that group. And then we also require, for physical reasons, in a sense, that each of the stabilizers has even weight. So it's a product of an even number of Majoranas. So given an embedded graph, the way we'll define our code is that we'll assign a Majorana to each half edge, and we'll also assign a Majorana to each odd degree vertex. And this is very reminiscent of how some of these models are solved by, for instance, Wen and Kataev. And this is also what Bravi, Engelbrecht, Koenig, and Paired do to simulate their surface codes with coherent errors. So this is really like a generalization of that to arbitrary graphs. And then, well, the final thing I need to tell you is how to define the stabilizers. So I just told you where to place the Majoranas, but we define the stabilizers as the product of Majoranas around every vertex and around every face. So for instance, in this picture over here, I draw the gray lines to sort of outline around the stabilizer around the vertex. So it's the product of all the Majoranas here. 1, 2, 3, 4. This is an odd degree, so it has 1 in the middle. This is an even degree, so it's just the product of these 6. And then also there's a stabilizer associated to the face, which is the product of all Majoranas around that face, excluding the odd degree ones. So if you draw the gray lines and you delete the parts of edges inside the gray, then you would get a new graph, and the stabilizers would be associated with the faces if you prefer that. We're not going to be working with this Majorana code for long. I just wanted to point out that it's a thing. We're going to transfer pretty quickly over to qubits. And the way to do this is to realize that, you know, around these vertices, there's a very simple Majorana code, which has a single stabilizer. And this code encodes this many qubits, where m is the degree of the vertex. So degree of the vertex minus 2 over 2. And so we'll just place that many qubits at the vertex, and that will sort of take care of this this Majorana stabilizer. So instead of representing this code space with Majoranas and a stabilizer, we'll represent it just with qubits. So this means that we place 1 qubit at degree 3 vertices, 1 qubit at degree 4 vertices, 2 qubits at degree 5, 2 qubits at degree 6, and so on. 3 qubits at degree 7. Yeah. And then you also have to assign Paulis around these vertices, and the stabilizers of this code will now be associated to faces. So let's talk about that a bit more. So the way we assign Paulis around these vertices is from something called a cyclically anti-commuting list. And this is just a list of polys, and adjacent elements in the list should anti-commute, and anything that's not adjacent will commute. So for instance, for degree 3 vertices, length 3, you have the list x, y, z. And then for length 4, you can choose x, z, x, z. These are legitimate CALs for lengths 3 and 4. So how do you actually go directly to the qubit surface code? You take your embedded graph, and then around every vertex, you write a CAL with length equal to the degree of that vertex. And then the faces of the graph represent your stabilizers. And those are just the product of all polys written within that face. So for instance, in this picture over here, there would be one big stabilizer from this face, and it would be, poly x on this qubit times poly y on this qubit times poly z on both of these qubits at this vertex, and then poly y on the qubit, one of the two qubits here, and then poly x on the qubit here. And should point out that in this paper, Homological Stabilizer Codes by Jonas Anderson, he defines something called label set, which is very similar, but it's just for degree 3 and 4 vertices. Right, so you might wonder, how do you construct CALs in general? Like I'm sort of claiming they exist, but here's the construction. So it's a construction, I should say. So for degree 3 and 4, clearly we have, x, y, z and x, z, x, z. For larger degrees, you can actually compose these degree 3 and 4 CALs together. So here's degree 7. There are 3 qubits here. You expand this out into 2 degree 4 vertices and 1 degree 3 vertex. You write the CALs around those. And then you just define, poly 0 here to be x on this qubit, poly 1 to be z and z here, and so on. So it's pretty simple just in terms of the degree 3 and 4 CALs. And likewise with L equals 8, now you just compose degree 4. Okay. An immediate question is, how many qubits does this surface code encode? And here's the answer. It depends both on the orientability of the manifold and also what we're calling the checkerboardability of the manifold. Or rather of the graph, I guess I should say. The graph is checkerboardable if its faces can be 2-colored. Another way of saying this is just that its dual graph is bipartite. And so using this property, you can prove this theorem basically by counting. If the graph is, well, all graphs actually, for all graphs, the product of all faces is identity. And then additionally, if it's checkerboardable, the product of just one color face, let's say the white faces, is identity. So in the checkerboardability case, you get sort of 2 stabilizers that are not independent from the rest, whereas in the non-checkerboardable case, you only get 1. That's how you get this term. I guess I should say explicitly that M is the number of odd degree vertices here. So you can see that the odd degree vertices are behaving as these twist defects. The more odd degree vertices you have, the more qubits you can encode. So yeah, let's jump into an example here to illustrate this. Let's start on the left here. This is just the rotated surface code. And I claim that this is not checkerboardable. This might this might be strange to you because normally you sort of do checkerboard it by alternatively coloring the faces. But the problem is that there's an outer face here as well. This is a code that's embedded onto the sphere. So the genus is 0. And if you just do this coloring, then you end up not knowing what to color the outer face, right? It's adjacent to both a black face and a white face. So this is not checkerboardable, and if you plug G equals 0 and M equals 4, because there are 4 odd degree vertices at the corners here, then you get 1 encoded qubit. And similarly, we can look at a code embedded on the torus and see that it's checkerboardable if it's even dimension by even dimension, and therefore it encodes 2 qubits. If it's odd by odd, however, then it is not checkerboardable. If we try to color the faces, then we'll end up not knowing what to color these faces. So something that we do to to mathematically make our lives easier is we do color anyway, and now some faces are adjacent faces are colored the same, and we introduce defects. And these defects are similar to what you see in Bombin, sometimes called domain walls. These are places where in our language, the faces on either side are colored the same. So it's a defect in the checkerboarding. And I'll just represent them with these stitched lines. So here's some examples of more codes. For instance, these cyclic torque codes. So the construction is somewhat easy to describe. You take the fundamental square region and you draw the lines y equals bx over a and y equals minus ax over b. So for instance, if a and b equals 1 and 2, then you get this graph where I drew these 2 lines and they intersect at these 5 points. This point is all the same, all identified. And this ends up being the 5-qubit code. So if you assign cyclically anti-commuting lists, then you see it's a 5-qubit code. And it's also a cyclic code because you can just shift stabilizers along the b over a direction. More generally, when you draw these lines, you get a code that has a squared plus b squared qubits. If the number of qubits is odd, then it's not checkerboardable and you get only 1 encoded qubit. The distance is a plus b. It takes some work to show this actually. And if n is even, you get 2 encoded qubits and the distance is max ab. So you can achieve kd squared over 2 in basically 2 ways. You can choose a equals b minus 1, or you can choose a equals 1 and make b odd. And some of these codes have appeared before, I should mention. Okay, so at this point you might be wondering, or maybe even before this point, what is the relation to the Kataev's model of surface codes, which I'll just refer to as like the homological model. So in this model, you place qubits on the edges of your embedded graph, and you define X-type stabilizers around the vertices and Z-type stabilizers around faces. So for instance, here, there's a graph on the projective plane. There are qubits on the edges. To get to our model, we wanna make sure that the stabilizers here correspond to faces. So we draw what's called the medial graph. So here in the dark colored lines are the edges of the medial graph. And so you can always take a homological code, draw the medial graph, and then you get an equivalent code defined in our model using the medial graph. And some important properties of medial graphs is that they're always checkerboardable. and medial graphs are always 4 regular. Their vertices are all degree 4. So if your graph has those properties, then it's a homological code. I should say it's if and only if. So if your graph has those properties, it's a homological code, but otherwise it's something that's outside this homological model. To continue with some examples here, I mentioned previously the stellated codes, of which the simple triangle code is an example. It turns out that both these fundamental polygons, the square where you identify opposite sides and the hexagon where you identify opposite sides, these both represent the torus. So if we place this triangular surface code on, you can see here that it's sort of hexagonal and we identify opposite sides. This is qubit 11. This is also qubit 11. This is qubit 8. This is also qubit 8, and so forth. Then we end up getting a 13-to-4 code. And generally, an n-gon with opposite sides identified will represent a genus n over 4, the floor of n over 4 surface. So if you take these stellated codes with higher order symmetries, they embed into higher genus manifolds. For instance, you can take the 32-to-5 and you get a 23-4-4. So the general pattern here is that you end up doubling the number of encoded qubits while slightly reducing the number of physical qubits. This reduction only comes from the fact that you're identifying qubits along the edges. So you're sort of losing order D physical qubits. And then you also reduce the distance by 1. And this is also from the fact that you're identifying qubits along the boundary. So in general, you actually achieve a better constant in this n proportional to kd squared. So for instance, because the stellated codes achieve n equals 1/2 kd squared, in the plane, if you're allowing higher genus surfaces, you can get arbitrarily close to 1/4 kd squared. And then example 3, there's 4 examples. Example 3 is this planar packing code is what I'm calling it for now. So the triangle code achieves 3/4 kd squared, as I said before. And we don't want to go to higher genus surfaces, maybe, like the stellated codes in the previous slide. So what can we do just in the plane? If these stars here represent the twist defects or the odd degree vertices, perhaps we can pack these in to the plane efficiently. So what does that look like? Well, here's the triangle code lattice. I'm going to just abstract away those details. So just draw it like this. We can extend the patch a bit. And now we encode 2 logical qubits, but n equals 5/8 kd squared. So 5/8 is less than 3/4. We already got an improvement. If we extend more, we encode 3 logical qubits and n equals 7/12 kd squared, and so on. So eventually you can approach 1/2 kd squared. And this 1/2 is the same that Hastings and Geller quote in their dense memory paper. And then finally, using our model of surface codes, we can come up with new hyperbolic codes. So hyperbolic codes, one way to think about constructing them, or it's really about constructing regular lattices, is that you start with this free group with a set of relations. And then to compactify this space, you need to actually find some normal subgroups which give you more relations. You can do this using computer algebra usually. And then yeah, and then you get a picture sort of like this, where you know, these edges on the boundary are identified. So this E edge is identified down here. And then if there's a prime here, that just means that the edge is identified non-orientably. So if one arrow is pointing clockwise, then the other arrow is also pointing clockwise. So using this, we can find some non-checkerboardable lattices, like this example here. And this turns out to be a 25-4 code. And it's something that would not be, you know, you cannot use it using the homological formalism because it's not checkerboardable, as mentioned before. And we can find some other small examples here as well of hyperbolic codes. Okay, so this is the extent of my examples, and I have like only a few minutes left to talk about distance. So I'm gonna just probably race through this pretty fast. So basically the distance bounds come from something called the decoding graph, where, you know, in degree 4, you're probably familiar with this from the surface code. In degree 3, you need 3 edges to represent, you know, poly X, Y, and Z on the qubit here. And then you can sort of generalize this where each edge represents one of the polys in the CAL around that vertex, the cyclically anticommuting list. And the utility of the decoding graph comes from the fact that, you know, cycles in the decoding graph represent polys that are in the centralizer of the stabilizer group. So for instance, in this code here, it has some odd degree vertices represented with the stars. The cycles represent, the green cycles, I should say, represent stabilizers, whereas the red and blue represent non-trivial logical operators. But in general, every cycle in the decoding graph, I didn't draw the full decoding graph here because it would get messy, but every cycle represents every element of the centralizer. Okay, so how do you use this to find the distance? Well, in the checkerboardable case, the decoding graph has 2 separate connected components, and these correspond to the 2 different colors of phases. So the decoding graph actually breaks into 2 pieces. You can think of it as X and Z if you like. And then the non-trivial logical operators are the homologically non-trivial cycles in that decoding graph. I mean, this is basically what Kataev tells us. In the non-checkerboardable case, though, the decoding graph, not only does it not break into 2 pieces, it also doesn't necessarily embed in the same manifold as the original graph. So that makes it hard to relate logical operators to some sort of homological non-triviality. So the doubled graph gets around this. It's a checkerboardable graph where either connected component of its decoding graph is isomorphic to the decoding graph of the original graph. And then we can actually say that non-trivial logical operators are homologically non-trivial cycles in this doubled graph's decoding graph. So how do you construct the doubled graph? Basically, you look at where your defects are. So for instance, if we have an odd by even square lattice in the tort code, you can cut along that defect and then take 2 copies. So this is after we cut, then we take 2 copies and glue them together along that cut. And so in this case, it happens that the graph G squared is also embedded on the torus, because we do this gluing and we get a torus back. More generally, that's not going to happen. So here's a genus 3 non-orientable manifold. It also has some odd degree vertices in the middle. If we go through this cutting and gluing procedure, we end up with a genus 6 non-orientable manifolds. The genus generally will increase, especially if you have some odd degree vertices. We can do this for the rotated toric code. This is, you know, obviously genus is 0, it's embedded in the plane. But then when we double it, it's embedded in the torus, actually. So here again is this hexagon where opposite sides are identified. Right, so the logical operators that you're familiar with for the toric code are these homologically non-trivial cycles in this doubled graphs decoding graph. And then we can also double the graph for the triangular surface code. Okay. So the theorem I just want to leave you with here is that the bound on the distance is given by this C systole, or the length of the shortest homologically non-trivial cycle. So if the graph is checkerboardable, then the systole of the decoding graph just gives you the distance. If the graph is not checkerboardable, then the distance is anywhere between the systole of the doubled graph's decoding graph or half of that. And the reason there's this half is because when you double the graph, there are two qubits or two vertices that both represent the same qubit from the original graph. And if you're able to take a path that goes through these two qubits, then its Pauli weight is just going to, its Pauli weight is going to be less than the length of this cycle, right? So in this case, the length of this cycle is 6, but the Pauli weight of the operator represents over here, when we map it back to the original graph, is only weight 5. So that's basically where this factor of 2 is coming from. And we have examples where that's tight. It's not hard to construct. Okay, so that's where I should leave you. I should note that this paper is coming out soon on the archive, and I'm happy to take questions.
Thanks, Ted, for a wonderful talk. We have time for some questions for Ted. I might start things off. So, okay, you went a little quick over the distance stuff.
Yeah, sorry.
Do I understand that the distance for the doubled graph, sorry, let me not talk about distance since you don't know the exact distance, but rather this C systole, the checkerboardable systole.
Yeah,
Can you
or
relate that
combinatorial system.
Oh, that's what's, okay, the combinatorial systole, sorry. Can you relate that for the doubled graph to the C systole of the original graph? Like, are there bounds that relate that?
Right, so well, I guess I should say C systole of what graph? So the C systole of the decoding graph in the non-checkerboardable case is not defined because, well, I mean, the checkerboardable graph or the non-checkerboardable graph doesn't have a decoding graph that embeds in the same manifold.
Okay, I guess the reason, what I'm wondering is if it's possible, like you have these like non-homology codes, and you know, people have been looking at homology codes as ways to approach things like quantum LDPC codes and things like this. Do you think that some of these constructions might give us new insights into the best distance achievable with sparse quantum codes?
Yeah, so I guess one consequence of this doubled construction is that if you look at the code defined on this doubled graph, it's now a checkerboardable code. And I suppose you also have to sort of break down these larger degree vertices using the CAL method that I showed before. But if you break them down into degree 4 vertices, then you get a checkerboardable 4-valent graph. And this is a homological code. So this doubled graph is a homological code. It encodes twice the number of logical qubits using twice the number of physical qubits. And its distance is, I want to get this direction correct. Its distance should be at least as good as the distance of the code you started with. Okay. So in terms of n equals kd squared, it's gonna have the same, if not better, constant than the non-checkerboardable code. But the non-checkerboardable code is going to be in a lower genus. So I think if you want to look for improvements, you kind of have to fix the genus, and then non-checkerboardable codes or these non-homological codes can give you an advantage, as we see with like the triangle code versus the rotated surface code in genus equals 0.
Okay. Other questions? Anyone want to ask a question for Ted? Everyone's shy. You can also ask questions in the Slack channel. And Ted's going to upload his slides to the Slack channel as well. So if there are no further questions, since this was the last talk of the conference, let's first thank Ted again for a wonderful talk. But I also want to thank my co-organizers, so Earl Campbell, Barbara Hall, and the non-local organizers, so Nicholas Kloikman and Yoshka Rofa and Boris Varbanov. They did a lot of really great work in organizing these Zoom sessions and things like this and making everything run really, really smoothly so that basically I didn't have to do anything except try to ask good questions from these speakers because everybody else was too shy. So I just want to thank you guys. And I want to also thank all the participants for coming out and making this a success, as successful as it could be over Zoom, I think. So thanks, everyone.